Okay, year 11, about to do a video on chapter 9 on theoretical probability, and we're going to have a look at exercises 903 and 904. So theoretical probability is when we've got something that we know all the number of outcomes to. So we did experimental probability, which was using statistical data or number of trials here previously, but now we're going to talk about things like rolling a die, tossing a coin, picking things out of hats where we have a set amount. So the first thing you need to understand what mutually exclusive events are. They're events that cannot occur at the same time or events that have no effect on one another. So they're used, for example, rolling a die and you can't get a 5 and a 6 at the same time. And they mention in it there. Whereas if you do something else that is not mutually exclusive, so you might be having a pack of cards and you might say, oh, picking a red card or a king. Well, there are actually 2 red kings. So a red card and a king are not mutually exclusive. There are 2 red kings. So that's an example of not mutually exclusive. Anyway, for mutually exclusive events, when we have the probability of A, and I like to use the word or when we're saying this, probability of A or B, we add the probabilities. Okay, so A or B. So let's have a look at some of these. I also need to mention this, and we know that if we have a probability of event equaling 0, that we say that that event is impossible, and a probability of event equaling 1, that that event is certain. So all probabilities lie between 0 and 1. And when you add up all the probabilities of mutually exclusive events, they will equal 1. And this one we mentioned in the last video, but we're going to explore it more here. The complement of an event is 1 minus the probability of the event not happening. So you need to write not this one, but this one. And I'd probably write, and you should know it, the probability of E equals 1 minus the probability of not E. And because that's an equation, you can write it the other way around. So the probability of not E equals 1 minus the probability of E. And to give you an example of that, the probability of it raining, so the probability of rain equals 30% on a certain day. The Bureau of Meteorology might say that there's a 30% chance of rain today. So what's the probability of it not raining? Well, you already do that in your head and you go, oh, well, 70%, whatever's left over. But the way that you should do it, the probability of not raining is 1 minus the probability of rain. This is just another way to think about it, which is 1 minus 30%. And 1 is 100%. So 100% minus 30% is 70%. Now, you don't go through all that, but sometimes when there's a whole lot of different probabilities that you can have, it's easier to work out the chance of something not happening and subtracting it from 1. But we'll come across those in a minute. Now, you don't have to do all of these questions. The even ones will suffice. And you need to know certain things. Like you need to know what's in a pack of cards. You can go and get pictures of that or screenshots of that and work it out. Tossing coins, rolling die or dice. They're all the things you need to know. So let's have a look at the first question. We've got a deck of cards. You need to know that in a deck of cards, there are 52 cards. We're not having jokers in our pack. There are 52 cards. And there are 4 suits, hearts, diamonds, spades, and clubs. There are 13 in each suit. So 13 cards in each suit. And the cards go ace, king, queen, jack, then 10, 9, 8, 7, 6, 5, 4, 3, 2. And then the ace also comes in as a 1, and there is an order to them. So, pack of 52 cards, one of which is the ace of diamonds. What's the probability that you pick the ace of diamonds? And remember, you don't have to write a lot for these. So here's question 2. The probability of an ace. Oh, there's only one ace of diamonds, 1 on 52. Oh, sorry, I should have said ace of diamonds there, not just ace, because there are 4 aces. So we'll put in ace and a little d for diamonds, ace of diamonds, 1 on 52. The probability of not an ace of diamonds, and you just write it like this. Now you don't have to say 1 minus 1 on 52. You can just say 51 on 52 if you do that in your head, but be careful with ones that happen later. And so on. I'm not going to do 4, 6, a bag of balls with only red and white balls. What's the probability of getting a white ball? Well, we go probability of a white ball. Well, how many white balls are there? 8. How many balls are there? 8 plus 6, 14. And you'd simplify that, but so on. I'm not going to do red. That's just as easy. Let's move on down here, have a look at some of these. Let's have a look at 10. The probability of a certain seed producing a plant with a pink flower is 7 or 9. So, what's the probability of seed producing a different colour? Well, probability of not pink is 1 minus the probability of pink. I want you to get used to knowing that. So it's 1 minus 7 on 9, which is 2 on 9. That's pretty easy. Now, expectation, and I should have written this before. How many would you expect? Well, expectation equals the probability of whatever it is. I'm going to write this a bit better. The expectation of an event equals the probability of that event times the number of, I'm just going to put S, the number of trials, samples, whatever that is. So here with this question, if 189 of these plants are grown, how many would you expect to have a pink flower? Well, I just go 7 on 9 times 189, because 7/9 of them are going to be that many. And that's 147. That's how many you would expect. Would you get that many? No, because this is theoretical probability. And when you're growing these flowers, I don't know, you might get 150, you might get 140. You might get 189 pink flowers. But the probability, based on whatever data they've got, is that you would expect 147. 12, a die, that's pretty easy. 14, let's have a look at 14. It's a little bit different. So a machine has a 1.5% chance of breaking down. Now remember, that's 1.5 over 100, so it's 0.15. You can do some other sort of breakdown if you want. What is the probability of the machine not breaking down? Well, the probability of the machine breaking down or not breaking down is 1 minus the probability of it breaking down. Well, that's 1 minus 1.5%, which is 98.5%. But if you use decimals, it would be 1 minus 0.015. I said 1.5 before, which is 0.985. Now, what's the second question? So, if 2,600 of these machines are manufactured, how many would you expect to break down? Okay, so what do we got? 2,600, so expect to break down is, what was it, 2,600? So 1.5 over 100, because it's a percent, times 2,600. And you expect 39 to break down. And you can see how companies would use this then, so they could manage their resources and say, right, we're going to need so many different technicians, because if we've got these machines operating in different companies, we're going to expect 39 breakdowns over whatever time period. We're going to need technicians to be able to do this. How many would you, or thinking about their insurance, how many would you expect not to break down? Well, you could just go 2,600 minus that 39. We're going to use the expectation, which is 98 point, oh, sorry, 98, fix that up, 98.5 over 100 times 2,600, which is 2,561. All right. I don't think I need to do any more on these. They're pretty simple. 22, remember we're not doing all of them. 24, the probability of 4 friends being chased. That's an interesting one, because they've left one out. If you add these 4 things up, you'll see that they don't add up to 1. That's important. All probability should add up to 1. Add those up, they don't add up to 1, they add up to 13. So something's missing. See if you can work it out. Okay. Interesting here, Girolamo Cardano. He was also very prevalent in introducing us to imaginary numbers. Interesting story if you get the chance to read about him. The big dude, Blaise Pascal and Pierre de Fermat. And you know Pascal's triangle. It has a lot to do with probability. Now, here we come to the one that we have talked about before. The addition rule of probability. So we've been doing that. Now, the addition rule of probability is when you add 2 different things. But the problem is you've got to be careful of counting twice, which is why we use Venn diagrams, or we use this rule. So the probability of A or B, I always say or when I see that, because it reminds me to add. So I'm going to give you an example. So the probability of rolling a dice, and getting a 2 or a 3. Okay, well, that's a probability of a 2 plus the probability of a 3, which is 1 on 6 plus 1 on 6, which is 2 on 6. Now that all makes sense. But what about if I take a pack of cards and the probability of a jack or a red card? So we're going to go that. Probability of jack and a red card. Okay, well, there are 4 jacks out of 52. And there are 26 red cards over 52. And you would like to think that that is therefore 30 out of 52. But that's not right, because there are 2 red jacks and you've counted them twice. You've counted them twice in here. Once in here and once in here. So you need to dismiss that. So we have to subtract those ones, one of those 2 that we counted twice. And the answer is 28 on 52. So that's what this law states. You've got to be careful of counting this bit twice. So you can either remember, so in your own notes, make this. You can illustrate it with a Venn diagram. And these are what we call non-mutually exclusive events. So they say overlapping, I say counting them twice. So let's have a look at some of these. Now, there are not very many of these. There are only 10, so I want you to have a go at them all. I'm not going to do them all. We'll start off with the first one. A number is chosen at random from 1 to 20. Find the probability that it will be divisible by 3. Okay. Well, the probability of divisible by 3, well, they're all divisible by 3. Yes, but we mean without a remainder. So my 3 times tables will mean, 3, 6, 9, 12, 15, 18. 1, 2, 3, 4, 5, 6. So there are 6 of the 20. So that one's pretty easy. B, less than 10 or divisible by 3. So I want less than 10 or divisible by 3. Now you could list them all. But you're going to get some overlap. So less than 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Gee, my writing is poor today. Let's fix these 3 up. 4, 6, 8, 9, 10. Okay. That one and that one and that one we've counted twice. So you can just go, 1, 2, 3, 4, 5, 6, 7, 8, already got that one, 9, 10, already got that one, 11, 12, 13. But you can just do this. It's 6 on 20 plus, hold on, less than 10. That one's not in it. 6 on 20, did it say less than or equal to? No, less than. 9 on 20, but you got to be careful, minus the 3 that we count twice. You've counted them twice. That's going to be 6 plus 9 is 15, minus 3, 12 on 20. Now, in the book, they just go, they don't even do that subtraction. They just count up all the ones and don't count twice. It's up to you. It doesn't matter. A composite number, remember, a composite number is a number that is not prime. Is 1 a composite number? No, I think 1's just a generator number. It's neither prime or composite. I wonder what they got for that. So the probability of composite the composite numbers, 2's prime, 3's prime, 4's not, 5's prime, 6 is not, 7's prime, 8 is not, 9 is not, 10 is not, 11's prime, 12's not, 13 is prime, 14 is not, 15 is not, 16 is not, 17's prime, 18's not, 19's prime, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, they got 11. So probably a composite 11 on 20. And the last question, composite or greater than 12? Well, greater than 12, that one is, that one is, that one is, that one is, that one is. We can't count them twice. And how many numbers are greater than 12? 13, 14, 15, 16, 17, 18, 19, and 20. So you can just go, I'll just make sure I don't count those other ones twice. Or you can do the probability of composite or greater than 12. Well, I'm just going to go, I've already got 11 on 20. I'm going to add these ones greater than 12. 1, 2, 3, 4, 5, 6, 7, 8. 8 on 20. And I'm going to minus the ones that I've counted twice. Well, there's 5 of those. And that's going to give me 11, take the 8 from the 5, 3, 14 on 20. But you can just go, I've listed them all anyway, so I'll just count the ones I need to know. And you could count 14. So it's up to you how you want to do them. I want to make this a quick one. So I'm just going to go along and have a look at some of the last ones. So I'll have a look at 9 and I'll have a look at 10. So question 9. A group of 75 students, so I would do a Venn diagram for this. As soon as I see these 75 students, I'm doing a Venn diagram. And this might be a good place to actually go, all right, let's see how one of these works. So I've got these 75 students. I'm going to draw my box there. What are they doing? They all study history or geography. So big circle for history and a big circle for geography. Altogether, 54 take history, 31 take geography. Find the probability that a student at random studies only. Well, I have to work out how many do both, because if I add those two together, I get 54, 31, that's 85. How am I going to find out how many do both? This is where you go. So the number who do history and geography, if I go 30, what was it? 31 plus 54, and I'm minus the 75. Now I have to be careful here. Did it say they all? Yes, all. Because there might have been some that don't study either. But luckily it said all, so I don't have to worry about that. So that gives me 85 minus 75, which means I have 10 kids who do both. So I got 10 in here. Now, how many do history? 54. Now, if I take 10 away from 54, it means I get 44 here. How many do geography? 31. If I take 10 away from 31, I get 21 in here. Now, it's always a good idea to check that this, and this add up to the total. And 44 plus 10 is 54, plus 21, 75. There are my number of students, and then you can answer the questions. So question 9, it was a good way to actually go through and create that Venn diagram. Okay, let's have a look at number 10. 20 dogs at obedience school. 14 dogs will walk to hill, 12 will stay. All dogs will do one or the other or both. So I'm going to do another Venn diagram. So there's my dogs. They'll walk to heel. This group will stay. How many dogs are there? 20. So how many walk and stay? Well, we'll add up two groups, 14 plus 12. 14 plus 12 minus, how many other dogs are there? Because they all do it, 20. Well, 14 plus 12 is 26 minus 20, 6. 6 dogs do both. How many walk? 14, which means 14 minus 6, that means 8 go in there. And how many, come on, move down. 12 will stay. So 12 minus 6 is 6. Now, those three numbers should add up to the number of dogs, which was 20. 6 and 6 is 12 plus 8, 20. And then you can answer the questions. So a Venn diagram is a really good way of doing those. You still have to work it out. You can see in their solutions, they do the same thing. So use those as a guide. But I think a Venn diagram is a much better way to do it. All right.